Seems recording. Yes, another draft physics video presentation. Sunday special. So some comments, all on the two slit kind of stuff for waves, and then I'll play an older video and just go through some more of the subject. Attempt to draw the distinction between these wave theories and the particle theories and why you should evolve, to the particle model. That the wave theory really is the old version, the broken version, in the sense of new observations make it implausible, and kind of how to get with the program. Anyway. So comments first. Oh shit, he mad. Yeah, that's just too interesting. Thank you. And we'll just remove it, but whatever. Why does it take so long? Anyway, thanks for your previous comments. Exclamation point. When you have just one slit instead of two slits, the one slit experiment, I think we can understand that. You shoot a photon through, the wave function gives a probability. Well, I'm arguing that that's just crap. There's no wave function, and the probability is like the outcome of scatter. Yes, it's unknowable with our instrumentality, but it's a real thing. Real things are hitting real things in real positions for where the photon will hit the screen. Yes, same would happen with scatter again. Supposedly the exact location is unknown prior to, well, like I said, it's unknown because we can't see photons traveling through the air, so therefore we can't videotape any of them or do any of that kind of stuff. So that's right, we don't know where they are. But there's no reason, no good reason to believe they don't have a real location. Hitting the screen due to the uncertainty principle, which is just absolute crap. That's why they call it a principle, not a law, is because they don't have enough evidence to even call it a principle. Q. In this case, why would the concept of superposition come into play? Well, again, I don't know why you're asking me to explain their theory. It's really not my obligation. Okay, let them explain it. Okay, so I don't think these are really important questions to why their theory is wrong. Okay, it's not the superposition part. It was the Heisenberg part. That uncertainty part is where you threw the game away. So why don't you ask them that question first? Assuming no entanglement. Why can't we think of the final position as unknown, like flipping a coin due to incomplete data? But again, they don't believe in the reason why they think the coin is actually doing something Heisenbergy, that it has something uncertain in its movement. And the wave function is simply a probability, and a measurement on the screen is just the outcome. Yes, well, the whole idea of this stupid wave function really isn't just some kind of tell you everything function. It's a function you have to explain everything to. The function doesn't mean anything unless you put all the variables into the function. The function doesn't predict anything without you already telling him what the answer is going to be. The function doesn't solve the equation. Knowing all the variables solves the equation. Anyway, meaning that we don't know the exact path of the photon took. Well, we know, again, this is group versus individual behavior. We know things behave in a certain way based on observing the group behavior. So we observe the roulette wheel 1,000 times, and then we can make some deductions about how the individuals function, because the end behavior of them over time is a certain result. But yeah, there's no reason to think that it's all happening by some magical God playing dice with the universe. So again, this is just back to the simple Einstein slur of just pointing out, well, what do you think? You think it's random? What, do you think there's some special force that's making the ball go to 22? But why should we believe that it could be all of those paths at once? Well, again, I suppose you're on my side here, but I don't know why you're asking the more complicated questions rather than getting to the core reason why polarization, for example, doesn't make any sense in terms of a wave function. Lots of things don't make sense. They can't be interpreted into their physics, the facts of them. And the whole idea of gluey mediums doesn't work. Okay, there's barriers to it making any sense. So I really just don't see the purpose of this. You're asking these questions like somebody else is going to answer them. They're not going to answer them. So why don't you say questions to commenters or something? Somebody who give a shit. Because they're obviously not questions I have to answer. Because I'm not speculating that any of that crap exists. So I guess I'd have to say, why are you doing this? Yeah, exactly. You're not making it clear who you're talking to and who you're asking the questions to. So do that next time. All right, JB at 2434, you say, or 2434, yeah. You said that photon polarization is almost as big as the slits. Yeah, I just pointed out a fact. Yeah, sorry for that. Yeah, I don't want to ruin your day. What a jerk. Polarization is not about size, it's about geometrical orientation. So what? I mean, how can you say it's not about size when it has a real size? It's a real fact. I mean, polarizing filters wouldn't work if the polarization could be this big or this big or this big or this big or any size they wanted to. Then photons would get through both filters. So clearly it matters what size the polarization is. So, what the fuck is your comment? It doesn't make any sense at all. It's clearly, I'm pointing out that if the damn thing has a certain size and has to fit through a hole that's the same size as it, well, that means that every single one that doesn't go right through the very center of the hole is going to get broken in some way. Pieces of its polarization are going to be broken off. And I'm arguing that actually means something. It's not some sort of, oh, it's so what? It doesn't matter. Photons don't care if you knock half their polarization off. It doesn't have a consequence. Well, it says you. With no evidence, no argument, no logic, no nothing. You just type this twat. It's just bullshit. So anyway, Enlightened Turtle, who's really a dumb ass. He's really a smelly, fat, stinking, slimy frog pretending to be a turtle. May the force be with you, Gary. And well, maybe you shove it up your ass until you're fucking dead. Alright, thinking clearly too. So he types the same comment twice, which is really something to annoy people on two different videos. Hello, Draft Science. Is it possible to engage a scientist in a private chat? Well, sure, it's possible, but to what advantage would it be for me? I'm arguing arguments they'll have no answer for. They can only rationalize. They can only come up with some sort of horseshit, just like the commenters do. Just like the guys who make these other videos and show you fake wave experiments or cite some other bullshit experiment. I go there and I show it's bullshit. So they're not going to do anything. I'm not going to get any right answers from those idiots. So what would be the point of it? But sure, I'm not opposed to it, but why would they do I should pay them for a private chat where I can't go, hey, that asshole said. If I can't point out what the asshole said, what's the point of it? Rather than in public on your channel. Well, I just don't see the point in it. If you can explain to me how I win that way, okay, but I don't see how I'm going to win a damn thing. Perhaps the people you have approached have been put off by the idea of going on YouTube. Well, again, I don't mind as long as they can say I make the conversation public. Where do they have to go on? They don't have to do video. They can do audio, fine. So you're, how limited are they in their functionality? Okay, I know you want them to be accountable, but it's worth having the conversation. It's not worth having it without accountability, frankly. The whole argument is they're wrong, and they've been promoting their physics as if they got the right answers, and they all know what the fuck they're talking about, and they've completely they've abused the evidence, abused the facts, they've quote mined the hell out of it, they've hyper exaggerated it. They're not unguilty here, and they deserve a little bit more than some sort of, well, let's have a private conversation about how you're crooks. What's the point in it? Because they're still not going to admit they're crooks. They're going to come up with some sort of bullshit evasions. They'll start talking about how messy my hair is. So anyway, I'll remove that, because who the hell needs this shit? Alright, then this other butthurt guy, blind.idiotgod. I thought about it a lot. You obviously know what you're doing. I didn't say I had the best strategy. I'm just saying I don't need backseat drivers who have absolutely nothing to go on but some intuitional bullshit they have. Why should I listen to your intuitional radar? Where have you proven you know anything about the subject of how to convince people of anything? I'm sure things are working according to your plan. Well, I'm sure I don't have any reason to change my plan because Joe Butthead in the back seat says, listen to me, I'm really an important guy, I know everything. Where's your evidence you know anything? I mean, if you had proven to me first how you really are damn smart, you have a lot of great strategies, and your life has been nothing but a fucking screaming success, then okay, maybe I'll take your advice, but that's not how you showed up here. You showed up here with a dopey screen name and a fucking cartoon icon. And you're saying, this is how you should do it, Gary. And I should say what to that? It's a fuck you. Alright, and I'm just too stupid to see it. Well, apparently you're too stupid to even figure out that if we reversed our roles here, you might be saying to, Draft Science, if he's commenting on your performance, saying how you're doing it wrong, and he has no explanation of how he ever did it right. How he's got, like, if I came here with 10,000 subscribers, 10,000, big fucking woo. What is the standard I'm supposed to be impressed by? You come here with absolutely nothing, a bag of big fucking empty, and you say, listen to me, I know how to find gold. See, I have no gold in my bag, but I know how to find it. I'm sorry I bothered you. No, well, you didn't just bother me. You made an argument that just didn't make any sense, and I'm supposed to sit there and, I have to waste my time trying to figure out whether it does make sense. And I found out, oh, shit, after evaluating, I figure it doesn't make any sense. There's really no value in this drivel. And that's my fault. Ugh. You injected yourself into the conversation as if you had something to say that was important. I demonstrated how I have no way of seeing its importance, and yet you're telling me it's important. Every time I hear a cop siren, I'm supposed to think they're coming for me? Yeah. I mean, there's some probability, but, it's not absolute. Alright, so anyway. So then this other guy links me to some nutball physicist. Well, he's not really a physicist. He's a neuroscientist, whatever the fuck those are. They seem to be all unemployed, frankly. But anyway, yes, I'll email him. But, he seems to be doing the seat of your pants kind of physics. Whatever he was told, he just is regurgitating. So I don't think he's going to have any solid knowledge about anything in particular, except maybe neurons, and I really don't want to talk about neurons in any depth. But anyway, we'll see. All right. Yeah. So that's it for the comments. So we'll do this old video, which I think is here. Yeah, here we go. So this is like the Royal Institution, somewhere in the 60s that they decided to video some of these things, which is really great. And the place all the scientists used to go. I don't know why they stopped doing this performance art, scientists. I think it was a good idea. Have a guy come in once a week and make an argument. And I don't know why they didn't video all of them, frankly, and whatever, but, blah, 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 blah. I guess a lot of them were just redundant. They'd come in and do the same show over and over, and everybody got kind of bored with that. But what you do notice is that there's all these experiments from the 50s, and they're all part of the lectures in the 2000s. So all the physics lectures done in the 2000s are just regurgitations of the experiments of the 50s, and like they've added nothing to them. And it's surprisingly like just redundant and unadvanced. So let's play along with this.
The nature of light. Huygens and his followers believed that light consisted of waves, and Huygens explained reflection and refraction by his wave picture of light. The other view was that light consisted of particles, bullets, shot out by the luminous body, which affected our eyes.
Right. So he points out that Huygens and Newton were the two main players, and Newton had no hard opinions. Newton wasn't certain of anything regarding wave or particle. So that's just sort of a lie that Newton was a particleist. He just wasn't a wavist. So I guess, but the only choice is a particle, right? So this is what the argument's about fundamentally, is that people would see something like the sun, and what do they think the sun is doing? Is it creating something that's coming off of the sun like this, you know, some sort of this thing, or is the sun doing this thing, you know, this ray thing? So it was really, the argument really wasn't about waves and particles. The argument was about rays and waves, right? Because both of these you could create with particles, right? I mean, I could send particles all at once, a whole bunch of little particles, and I could make waves by just sending a bunch of particles. Just go blah, 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 you know, a whole bunch of shit comes out of my mouth. That could be, you know, particles of whatever, snot or something, right? I could just blow stuff out of my orifices, and you could understand that, okay, there were waves of sneezes, right? I could sneeze, achoo, 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 right? And there could be waves of little droplets of coronavirus or whatever. So you can understand particles can make waves, and you can certainly understand that a particle could just go from here, shoot in a straight line, and end up here, and that would be a ray. So the real argument was rays versus whatever these benty line things are. Okay, so, but again, this thing, if I make it out of particles, is the same thing as this thing, right? You're just saying it's pulsing, so the ray is pulsing, so the ray goes on, it shoots a bullet, it shoots a bullet, it shoots a bullet, so one bullet's here, and then one bullet's here, and one bullet's here, and one bullet's here. So the controversy got lost in the vocabulary, really, you know, in how you describe the different ways that you can produce this. So the thing underlying this is this idea of whether something's going to go from point A to point B. And the idea is people believed you needed to have a whole bunch of, you know, points, you know, A point 1, A point 2, A point 3. Like you have to have a whole bunch of cue balls lined up here. And so you hit this ball, it goes through all of these, and then it pops out this end. So that somehow we need an infrastructure to pass the compression through. And other people would just say, no, you just hit this one and this one will roll, okay, all the way to point B. And so you don't need anything in between. You don't need any dominoes to fall, okay, to transmit a signal. That a signal can just, one domino can just flip over here, or you need, oh, I gotta knock this one down, knock this one down, knock this one down. So those are really the competing theories. It's really the theory between space being empty and momentum being something that moves through the space. Like actually a thing, okay, starts at point A, and the A thing actually goes to point B. It's still the A thing here, and now it's at point B, you know, that kind of thing. It doesn't need to transmit a bunch of other stuff to get point B to go, I got the message. So that's all that's in competition here. And if you're honest and you're looking for the truth, there's reasons to believe one and reasons to believe the other. But I'm arguing if you put all of the facts together, I think it'll be demonstrated that the viable theory is this one. Okay, the bits just moving through an empty space. And the unviable theory is the idea that you have this glue that you're going to push things through, you know, have a vibration through. Because for lots of reasons that I have articulated to no avail, unfortunately. So anyway, so that's sort of the starting point, is that this isn't about wave-particle duality, it's about wave-ray duality. It isn't about that, it's more about an ether versus an empty space theory of the universe. That there's some things that move in the nothing. Not that it's all a something and then there's something else's, and the something else's move in the something.
Newton had upheld the particle theory.
Upheld? He didn't really, but anyway, go ahead. You can say it if you want, but I don't think that's true.
In justice to him, it must be recognized that he did so very tentatively.
There you go. So he didn't have a hard opinion. He didn't have any way of explaining all the phenomenon at that time. There was conflicting information from his perspective. Now let's understand, he didn't know a lot of stuff. Didn't know about polarization and frequency. Didn't know what electrons and protons were. So a lot of limitations to what he could assume about functions.
He never expressed himself as quite sure, but on the whole he thought that particle theory was probably the right one.
Now, on the whole, he thought wave theory wasn't, but whatever. I'd say he was more against wave theory than pro particle theory. Because he just didn't think waves do some obvious things that it seemed obvious light wasn't doing. That if light was a medium of things that, like water molecules that were attached to each other, that the truth is when you sent them through the single impediment, if I put a little needle in the way, that they should, in fact, recreate, the wave and all that kind of stuff. And it seemed obvious that, you could put certain impediments in front of it and it wouldn't reconstruct the wave. It would make a shadow, and a hard shadow.
And Newton's followers were far more convinced than Newton was himself. Now, towards the end of that century, a famous experiment was made by Thomas Young, Young's pinhole experiment.
No, it really wasn't the end of that century. It was the beginning of the next, because 1801, but whatever.
Which proved that the wave theory was the right one.
Okay, so he says it, right? He says it proved that wave theory was the right one. It really didn't do that, and it didn't add any information that Newton hadn't already discovered. So let's understand, Newton had already done this experiment, impediment. He'd already done the slit, okay? So he had done the facing each other experiment and the surfaces going out experiment, essentially. And so he knew what the rings were, knew what all that was, didn't have a theory, though.
Because he showed that light could interfere.
So he didn't show that it could interfere. He just showed that it created an on-off pattern. And an on-off pattern is what they said, okay, that's sort of like interference does on-off too. But again, a scientist would know, well, on-off is the simplest pattern in the universe, and I have to be very careful about thinking that on-off is always interference, because it doesn't have to be. I mean, a spinning wheel with a little notch on it can create on and off. It's not interfering with anything.
This Young was a very remarkable man. He was a doctor, practicing doctor. He had other literary and scientific interests. It was he who found first the key to interpret the Egyptian hieroglyphics. He had done a great deal of work on capillarity or surface tension, on elasticity. Some of you may remember Young's modulus of elasticity. He was one of the first to uphold the three-color theory of color vision.
Yeah, really, all very good stuff. I mean, the whole color blindness subject and everything, really a lot of stuff. Well, Rutherford had done that too. So it is kind of funny how they do cross some disciplines. Faraday did a lot of stuff on color vision, color blindness.
And above all, what is so very famous, he did this pinhole experiment, which could only be interpreted if light consisted of waves.
So again, this assertion, it could only be interpreted, and it's just not the truth. I mean, and scientists should know they can't say stuff like it can only be interpreted this way unless they somehow, number one, conceived of all the other interpretations, all the other ways it could be viewed, and found them all to be lacking. I mean, it's an extraordinarily bold statement to say that it's not, possible when you think of what particles are capable of doing. I mean, particles have a lot of diversity in terms of how you can arrange them, where waves are kind of rigid. I mean, you can't do much with waves because they do have certain rules of their function, the consistency of the way the energy is balanced over the wave, and all these are kind of rigid where particles can do all kinds of, they can be this big, they can, they can be longer than they are tall, they can be lots of different things, where waves really can't. And so to say that somehow they eliminated all possibility that we could interpret, especially a phenomenon as simple as the single aperture, the single hole experiment where you send the photon in and you get the, a pattern of rings out, which equals this idea. When, you could just, like I said, surmise the obvious that as I make the hole smaller, then I'm increasing the likelihood that the photon's going near the edge of the surface, and then it's really kind of intuitive to say, well, the surface could cause it to scatter, and it could go to all kinds of locations. But the only location I'm going to be able to see it at has to have the right geometry. The scattered bits have to come here and reconstruct a photon, or I'm not going to see anything. So, it's not that complicated a theory that does fit. And he's basically saying that somehow they had some reason to believe they excluded that theory. It's not even a complicated theory, And how did they exclude it? How did they say it can't be? Oh, that's right, they didn't come close to that obligation. So they're just quote mining the experiments. They're just saying what experiments make it look like it's a wave, and we'll go with that. And in any experiment that, or any model or drawing that can illustrate another way to do it, we just pretend it doesn't exist. That's all it comes down to.
Now, let me try with this diagram to show you what Young's principle of interference means. And let's take Young's original pinhole experiment. He made a pinhole in a screen and illuminated it with sunlight, the brightest light he knew. And here, on his wave theory, we must suppose that these waves are coming from the pinhole here, spreading out in this direction.
Right. Now, so I just had this argument with people who are saying that's not accurate. So Young, the sound engineer, the doctor, didn't know how waves really work, because that's not what waves do when they go through an aperture. Regular water waves or sound waves. And yes, that is what they do. So they just make a solid wave. They don't make a whole bunch of on-off pattern.
In the path of these waves, he put two slits, two pinholes, rather, and the waves were allowed to come through those pinholes. So in this space here, one had two sets of waves, one coming from that pinhole.
Right. So there's no theory that says, oh, okay, the first pinhole is creating interference, and we send interference into the double slit. Right? They don't think so. They think they're nice, plain, flat waves. And they have a distance between the pinholes, so the waves are now getting flatter and flatter as they get bigger and bigger. And so there's no theory that a single pinhole creates interference. So you can't have it both ways. That's sort of making a scientific mistake, is when you have two contradictory explanations. 1 minute, the single slit is making an interference pattern, the next minute it's not. That can't be that way.
One coming from that one. Here they are. And now, perhaps you can see what interference means. Young argued that at a place like this, where the two sets of waves have crests and troughs that agree with each other, in step as it were, the light will be bright.
Okay, so the point is, though, is that now, it was okay in 1801 for them not to realize what the real double slit pattern was. So we know now what the real pattern is, okay? The real pattern isn't just on, off, on, off, on, off, on, off. The real pattern is, and you got these places where there's this extra off, okay? So, the extra offs is the bit, okay, that you also have to explain. And there's, no theory I've seen where you can explain how two symmetrical waves, two equal waves from two equal slits can possibly create that pattern. So you can do this crisscrossing for 200 years since young. They've been doing this, and they're not going to create this, and they're not going to create that. So this doesn't satisfy the real experiment, doesn't satisfy what we know to be a fact. So you have to modify this to create that. And there's no modifications that work. And the only modification that turns out to work is getting rid of these waves, okay, and recognizing that the real point sources are the surfaces. Okay, the real point sources are these locations, and so if you simply apply the logic of adding the two rays that come from here and move those to all these different possible locations where they complement each other in terms of being a wavelength difference in their a wavelength difference, you'll get this pattern, and then you'll get this pattern. So you'll get these little humps, okay, of the double slit experiment. And then if you take these 2 point sources and do the same math, figure out where they complement each other, okay, you'll find out that these two sources create a bunch of little waves, bars, and that those bars will be on top of the envelope, and that all you're really doing is adding this to this bar, and that produces enough light to create a photon. So you see it where it has extra light pumping it, and you don't see it where there isn't enough extra to make this visible. So these become invisible where there's nothing added by the first two slits. If they don't add enough, you don't see anything. And it's only where they add enough photon energy do you actually see the photons. So this works. So, and this, obviously, you wouldn't draw the waves here. You wouldn't draw waves on these points or these surfaces. That wouldn't make any sense. There's no wave theory that can explain, none that I've heard. I've heard no wave theory that would explain why the waves would be halfway over the surfaces. So, the end of the wave would be in the middle of the opening. There's no explanation that makes that make any sense. So, but yes, as particles getting closer to surfaces, yes, it does make sense that these photons that go near the surface are the photons that are actually going to these locations. So again, this drawing is 200 years old, and it's for 200 years it's been wrong in the terms of it doesn't create the right pattern. It doesn't work.
Where the crests and troughs just interleave each other like this, the crest of one destroys the trough of the other, and there's nothing. Out here again, they agree, and it's right. So Young said, my fringes, my dark and light stripes, where the light overlaps, are caused by the interference of these waves. Light, dark, light, dark, light.
Right. But again, their example also has the lack of fineness, also that creates these little tiny bars of light, because that's not what, you obviously don't see, the light spots don't represent where there's a higher amplitude, that is where you're mixing, where you're adding two humps or where you're adding two troughs. So you're not getting this huge differential to make a photon. So it really is an on, which means that the energy to make the on has to come from where the offs are, and somehow, and there's no theory for how a wave could do that. Where does the energy go when it's destroyed, kind of argument.
And so on. No light is ever lost. You gain here where they agree just as much as you lose here where they don't agree. But the light...
Not really the truth. There's places where there's no wave, that is no energy, and then places where the energy is both high on and then high off. The high, strong trough, strong peak. which doesn't describe, again, photons. Photons aren't made out of something going positive and something going in some sense negative.
Splits itself up into these two sets. And Young said this must mean that light's waves and not little bullets or particles.
So if Young had the right pattern, then he wouldn't be able to argue it must mean, because then he'd be able to see that, oh yeah, it doesn't match the real pattern. So if they had a better picture of the pattern, better optics to make the pattern more revealing, Young couldn't really make the argument, right? Because the two waves won't create the right pattern. So all of this controversy, right? We put the nail in the coffin 200 years ago. Well, obviously anybody honest should say, well, that's a nail we should pull out. And yeah, maybe we can hammer it back in again. But first, let's do it honestly. First, let's pull that nail out and admit we're not getting the right pattern. That should be your first obligation as a scientist, is to say we should never nail that coffin shut because that was the wrong pattern. Is that asking too much from physics to admit that 200 years ago they were matching the wrong pattern? I mean, it's a fact. They just refuse to admit it. And obviously you can't say your nail in the coffin evidence shouldn't be describing the wrong pattern, right? If you're going to say it's nail in the coffin evidence, this is supposed to be really good evidence. Really good evidence shouldn't have, it's like if you say that it's a 45 caliber gun, but the gun on the witness stand is a 38, you can't get away with that. That's too big a flaw in the connection between your theory and the evidence. So they should at least be able to admit this, and they won't admit anything. And that's what's just showing how this is a conspiracy of hatred of the truth. I mean, a real contempt for the logical process, for the scientific method. They hate the scientific method. They hate the truth, because that can only be. Who would deny it? It's overt that they nailed the coffin way too soon, 200 years too early. And they still, right now, don't have an explanation for those stupid blank spots. And their only explanation is a mathematical model that completely confirms the particle theory, because they have to move the point sources to the surfaces. The surfaces are what's causing all the action. They're the point sources. So the evidence is the opposite evidence. The evidence is stronger for the particle model. And yet they're insisting they nailed that coffin 200 years ago and they did it well. No, they did it really badly, with really bad evidence.
Couldn't get two sets of bullets interfering with each other and cutting each other out. But you...
Right, of course, bullets don't interfere with each other. That's exactly right. Forces don't interfere with forces, and so we already knew that too. So this was, Young is after Maxwell. We already know, okay, some of the Maxwell rules of life, and we know that the forces really don't interact with each other. So why are we pretending light can? All the other stuff going the speed of light force does not act on force. Force has to act on matter. So why are we assuming that bullets can bang into bullets or waves can bang into waves? Because neither one shows any evidence of being true. I can shoot laser beams at each other all day long, and I can't get the photons to bounce off of each other. It just doesn't happen. The best I can do is have some particles in the field and have the lucky circumstance of two photons hitting the same bit of dust at the same time, but that's all you do.
Can get it with waves. Here then is Young's picture of the effect which he drew when he wrote up a set of lectures which he'd given. The waves are coming in through these two pinholes.
Right, so a 200-year-old drawing that they're still using today that produces the wrong pattern. And this is called good science. So for 200 years, we just leave it wrong. I mean, I don't know when they first discovered the second pattern. By doing the experiment with lasers is probably when they noticed that. But somebody might have noticed it sooner. And this is a real problem. And they just completely pretend it doesn't exist as a real problem, when it's a real problem for that two-wave theory. That two-wave theory won't do it. Two-symmetrical wave theory.
Here, A and B, they are spreading out in this direction, and you'll see all along these tracks there are places where the troughs and the crests alternate so that we get nothing, and places in between where they lie on top of each other where you get a strong effect. So you get these stripes of darkness and light spreading out from here, and when they fall on the screen, you'll get dark fringes at C, D, E, and F, and bright fringes in between. Now,
So again, we'll just say that, yeah, that was true in 1801, but it's not true now. So fix it, because it's not right.
Young explained his principle by his wave trough, by making a trough in which he could set up waves. And again I have here a picture from Young's book. Here is his source of illumination. Here is his tank filled with water, which has a glass bottom. Here.
So let's understand that Young wasn't just a believer in waves, he was a believer in ether, okay? Because he believed that light was traveling through something like water, where the bits are connected to each other, and that which causes distortions in the movement or the migration of the whatever, the photon. So in spite of all the evidence we have that you can single photons fly through space, there's not a wave of them, that it's an element that lands on a tiny piece of a surface, and stimulates it and creates electricity on a tiny, tiny bit of surface. In spite of all the evidence that it's a discrete thing, he believed it was some sort of, it moved the entire ether. One photon was something going everywhere, even though it landed in one place. Because there's no way to make a wave do that. You can't make a laser beam wave. You can't do it in a medium. A medium will spread the wave to all kinds of bizarre locations that it shouldn't be going.
Is the dipper on a spring which vibrated and made the waves, and the shadows of these waves were thrown by the light through the glass bottom onto this screen here. So he could set up waves and see how they behave. We've got here Young's original wave trough, dating in the year 1800, when he was a professor in the Royal Institution. There is the trough, there's a bright light down below, at the back is a mirror, and in front there is a screen on which we can see the waves. Now, if you could just...
So he's not using slits, he's just tapping the water, and, that's about as rudimentary as just throwing rocks in a pond, and it's almost like the kind of thing you don't need to go to this much trouble to illustrate because, everybody's seen it. Everybody can just have a pot of water and just stick a knife in it and see the waves. They really don't have to go to all this trouble.
To dim down the light, I want to show you Young's wave trough working. I think you can see the shadows of the two dippers, which are like Young's two pinholes. Now, we'll set those going. They'll send out waves. And I hope you can see spreading out the bright and dark fringes exactly as in Young's picture.
Yes, he drew it mostly accurately, I suppose you could argue, but yes, it's pretty simple to draw. The basic function, but you even do see the distortion that takes place in a medium. A medium is going to distort, and that's why some of the pieces of the wave are going straight, is because nature's going to try to find the shortest path in the process of doing that annihilation and that addition. So it's not as perfect in a sense as the drawings, because the reality does make straight lines.
Now, if I could have the lights on again, please. This is so important a principle, I'd like to illustrate it in another way, with sound this time. I've got here two speakers, and by making the connection here, I can make those both sound at a very high frequency.
So again, this is waves in a medium. So it's not just about the fact that it looks like a wave. It's about the concept that the medium is sticky, that it has the pieces of the medium have to move collectively. They can't move as individuals. And that's what all this is dependent on. So for sound and water, they both are traveling through a medium where the bits don't have freedom.
They are in parallel, so they are beating in unison like the light coming through those two pinholes. Two sets of waves are coming out. They will cross over where Mr. Coates is over there, and I hope when he moves the microphone he's holding backwards and forwards, you can hear it passing through the places where the sound is strong and where it is weak. The sound fringes, if we like to put it in that way.
So this part is completely consistent. Yes, sound is like water. The argument is that light isn't like water. It's not traveling through a sticky medium.
Now perhaps we might run through them rather more quickly. There, I hope you heard these sound beats. Now,
right, exactly. Called beats for a reason, because it's where the harmonics are piling up. But anyway, bouncing off all kinds of different surfaces and whatnot too are often add to those. So those are sound experiments are a little bit dangerous because the sound's bouncing off all the surfaces. And so you're just adding harmonics. So a lot of times you can be tricked by those kind of experiments, frankly.
Try and demonstrate the same effect in a rather amusing way with a sensitive flame. I'll switch off the speakers for a moment and show you how this flame works. I've got here a flame which is almost on the point of roaring. It's just not. And any sort of high note makes it roar, as you may have noticed while I'm speaking. It just rattled the cash in my hand.
Yeah, so it's hard to imagine what the exact purpose is, but yes, fine. I mean, it's a nice instrument, creating a little gas valve that's somehow capable of closing off gas at the same rate at which it's hearing sounds.
Sister Susie sewing shirts for soldiers. You see how it dips every time at the high-pitched S noise. Well, we'll switch on the two speakers again. They will form a fringe field over in the neighborhood of that flame. And now...
So let's understand, waves, that are in sticky mediums can add up to different things. So if it's doing this, it can add it up and turn it into nothing. But the argument is that you can't do that to a photon. There's no medium where you can say the photon is, and then there's some other kind of photon. A non-is photon. The photon really is just made out of stuff that's either is or isn't. The frequency is made by having stuff and then having no stuff and then having stuff and then having no stuff. That's what the wave is made out of. And you can't mix stuff and no stuff and get no stuff. There's still stuff. You can't make the stuff go away.
As Mr. Coates moves the flame backwards and forwards, we will see the flame ducking up and down as it goes through the light and dark fringes, the points of high intensity and low intensity. Right.
So just to be clear, water and air are functioning in parallel. It's parallel systems. They're both molecular and they're both molecules in confinement, molecules that don't have any freedom.
You will have seen how the flame ducked down and went high again as Mr. Coates moved it through the fringes caused due to interference from these two sources. Well, now, I want to show you Young's famous experiment of getting diffraction fringes with light, and so establishing the wave theory of light. We're going to use slits instead of pinholes. It's fair to do so because if you look at my diagram here, you realize that if there's a slit here and two parallel slits here, you can regard this as a series of pinholes, and they all form their fringes on top of each other, so you get them in the same position and reinforcing each other. We're using...
So he's just arguing that obviously you want to increase the... It's not a very good argument. He's just arguing for getting rid of the round edges of the surface. But, you know, he's sort of implying that, you know, you could... Well, you really can't do it the way he's arguing anyway. Point is if you have a hole, you have this, and this is a rounded surface, and so it's going to create who knows what kind of added creepiness to your function. So what you're really trying to do is say, let's send light here, 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 across a lot of surface. So it's the same thing as this. It's just that, yeah, it's better to cut this off, just so you can maximize the effect in this one dimension.
Slits instead of pinholes because you get so much more light. When one realizes how...
No, it's not that you get so much more. You just, you know, I mean, obviously, as you're cutting these two sides off, you can extend this length. So that's the argument. You can make it longer by cutting these sides off. So then you can make a smaller measurement, the light fill a larger area by using a slit. That's really not the key to the experiment or the key to making it look better. The key is that you're getting rid of roundnesses on all of the surfaces that just makes the little blobs of light less visible what they're doing. So Young's original experiment looked like this. This is what Young saw. Okay, in white light, which means, you know, this was reddish, this got bluish, this got reddish, bluish, you know. It was all a bit of a mess.
How difficult it is to set up this Young experiment. One can't but admire Young for having done it originally. Instead of the sun, as Young used, we're using an arc lamp there. The coast is now turning that on, and in front of that arc lamp is an extremely fine slit. Here, about 8 feet away, we've got...
So let's understand, nobody bothers with that anymore. I don't even know exactly what purpose it served in the original experiment, except to guarantee you have light that is in phase. So the experiment is you have your light source, and you put a tiny hole here to basically cone your light, you know, to make this thing happen, to create a narrow beam of light. But the real key is what you're preventing is these longer rays from screwing things up, I would assume, because they would be out of phase. So you're trying to eliminate the longer rays by forcing the rays this way and trying to collect as much of the light that goes through the center as possible, because that won't be the bent light. The bent light is unlikely to hit the center, so you have less bent light in the center, so then it's all in phase light before you get to the two slits. So I think that was the real purpose of this aperture, but nobody bothers with that with a laser, because laser beams are already, generally speaking, in phase. So they just shoot the laser at the two slits. Okay, and don't bother with the aperture.
Two slits, again very close together, about 1 millimeter apart. And there's a shutter in front of one of them. I can open it.
So about 1 millimeter apart, right? He just said. So let's understand, when people talk about the wavelength of the light, oh, the slit has to be the wavelength of the light, or the opening, or whatever. And you're saying, no, it doesn't. The impediment doesn't have to be tiny, and neither do the slits have to be tiny. I mean, 0.5 millimeters more than, you know, is good. So it has nothing to do with the wavelength of the light. You don't make slits that are 500 nanometers. So I don't even know why they started saying that kind of stuff, because it makes no sense at all. So this is correct. Half millimeter works.
By turning this knob here, bearing both slits, or close it, leaving only one slit open. We'll see the fringes over in the distance on my right. We have to use slits very close together indeed, and look at the fringes at a distance, because you must remember how short the wavelength of light is. There are about 40 to 50,000 light waves in an inch. Again, we admire Young having got the effect with a very crude apparatus at his disposal. So now...
Right, so again, Newton had even cruder apparatus, more than 100 years earlier, so let's give credit where credit's due. Newton first, because frankly he did all the elements of the experiment.
I go over here with this piece of ground glass. I'll place myself so that the fringes fall on my ground glass, and with the slits as close as this, in spite of the short wavelength of light, the fringes will be far enough to see with the naked eye.
You can see them with your fingers. So, yeah. You can see them in the form he's going to see them in, which isn't it isn't the normal pattern.
Well, now I've placed myself in the line of the optical bench. So if I could have the lights down now, please. When I hold up my ground glass, what I see here is the image cast by a single slit. It's a white patch of light, and on either side of it there are colored fringes.
Okay, so he's obviously looking at white light, so the light is going to different locations and it's dim, so we don't see it, but he's seeing the red line, and then he's seeing a blue line, and then a red line and a blue line, that kind of thing. So, how much value that has there. That we know with a single slit what it makes is a pattern, and especially at those dimensions, something like a half millimeter slit, single slit, is going to create really a lot of little lines.
Called diffraction fringes. These have nothing what...
See, you call them diffraction fringes. Now, Professor Lewin would point out they're no different than the interference fringes. Fringes are fringes, and they're only caused by interference. There's no such thing as a diffraction fringe. Diffraction can't do it. It needs to be interference to create the on-off pattern. Diffraction doesn't have any mechanism to create the interference that causes on and off.
Never to do with Young's effect.
So he just says they don't have anything to do with it. Well, Professor Lewin would say otherwise. Same effect, same cause, and I would argue likewise it is the same cause, and the simple argument is the surfaces cause the effect. This is all about surfaces, not slits, not impediments.
A more complex effect that you get when light passes through a narrow slit. But now, if I ask Mr. Coates to uncover the second slit, its patch of light falls on top of the first one, and I can see that the patch is covered with beautiful...
So we didn't get to see the actual process, which would have been nice to see exactly what he saw when one was opened and one was closed. But you can see it's obviously twice the size almost. So it's gotten much larger, the image you get. So the two slits have, in some sense, produced more light, obviously. And again, this pattern is the pattern happening inside the slit. So we're not the usual pattern is one broadcast away from the slits, not inside the slit. So he's trying to see the amount of scatter going on the inside. You obviously can't see it going inside because it goes inside. It self-destructs. So you can only see what's on the inside, which is just a tiny fraction really of the pattern that would be magnified going the other way. So it's not a great, even though he's seeing a magnified view inside the tiny slit, he's looking, I don't even know how to say it exactly. he's looking at what would have been projected, but he's projecting it inside a smaller surface, so it's not as easy to see. And so if he could get it projected all the way out, he might have seen that it goes, 7 bars in the middle, and then it goes to nothing, and then it adds 5 bars, and then it goes to nothing, and then it adds 3 bars. He would have seen the real double slit pattern.
Irregular, fine, black and white fringes.
And they really aren't, right? They're clearly on-offs, right? You don't even see any graduation at all in this pattern. You see little little lines, and they get very gray. It's quite obvious, right? So why are they getting grayer when there's supposed to be less photons, right? So you're going towards the outside where there's supposed to be less photons, so the dark lines should be darker on the outside, and they should be lighter on the inside. And it's completely reversed, right? I mean, the dark lines are darker on the middle than they are towards the fringe edges. Why does that make any sense, right? So it doesn't. The theory is wrong.
These are the actual Young's fringes, which he observed and so proved the wave theory of light.
Well, says you. Okay, that's what he observed. Apparently he just didn't keep enough notes for anybody to know exactly what he did, whether he viewed as this guy is viewing, or whether he projected it on a surface and viewed the projection. I'm arguing that the evidence I've seen of some image he drew was of these circles. So he did see the pattern projected.
Now, why were scientists so reluctant to believe in the wave theory of light?
So I don't know if that's, they're reluctant to believe in ether because they had all this evidence of particles in quanta that were also showing up. So all the electricity and charge and all those things were demonstrating that everything was, forces didn't interact with forces, that the ray nature, the inverse square law, rigidities, all these kind of things didn't go with bendy, wavy things.
Is because of the sharpness of shadows. They could not understand how light, if it was waves, could cast such very sharp shadows. We don't often see these sharp shadows because most sources of light to which we're accustomed are rather broad, so that the shadows are fuzzy.
No, they're rather multi-source, okay? We're seeing a lot of reflected light also cast on the object, so the shadows are fudgy because there's different sources that are shooting from different angles.
But if we have a really fine source of light, like I've got here, and now if Mr. Coates positions it to cast its light on this screen, and I switch it on, and now if Mr. Coates holds up his arm in front of the screen, I want you to see how sharp those details are.
Right. You can see how sharp the details are by these little tiny hairs that aren't creating any kind of, you can see them and they're clearly visible and they don't get washed out by light going around the hairs and doing all of the stuff it's supposed to be doing because there's enough angular precision for there to be dark shadows, so it doesn't fill in all of those gaps, and those should be very small gaps even for a photon. Photon should go around a hair pretty easily. It does in laser experiments, so if you cast enough light on it you can wipe out those hairs, but that's the only way you wipe them out is by volume alone.
Although his arm is quite a long way away from the screen. That is the effect which puzzled them so much.
Well, I don't think that was the whole story, but whatever. Like I said, this is all in the context of when did they start to make this decision, and I say they stayed quite indecisive long after Young. And it wasn't until the 1900s, and then Einstein and all this other crap that they all jumped on the wave bandwagon.
Could I have the lights up now, please? Now, they couldn't believe that waves could cast shadows like that. Young himself couldn't understand it, although he believed in the wave theory of light. It was left later to the great Fresnel to explain.
Okay, so, he's conceding that Young couldn't even explain that. So there's at least that's a good admission, right? If Young actually admitted some pause, that would be fine. I don't know how much pause he actually admitted, though.
explain how it happened.
Right, and that explanation ends up turning the waves into point sources, and they're not in the right place. So the theory is kind of blown up by the fact that you've changed the two slit into 4 waves, not 2 waves, or 4 point sources. And the point sources don't line up with where the waves are supposed to be going through the slits. So that's troublesome, isn't it?
The answer is that the shadows are so sharp with light because the wavelength of light is so extremely short compared with the size of the objects that are casting the shadow.
So again, let's understand, a human hair is pretty small, 500 nanometers, well within, they're similarly small things.
If we have very short waves compared with the size of the obstacle, then you get a sharp shadow behind that obstacle. If, on the other hand, the waves are long compared with the size of the obstacle, for instance, sound waves, which go round corners quite easily, then the waves bend right into the shadow, and in fact the obstacle hardly makes any difference. The waves seem to heal themselves as they go past it.
Right, so this seems quite contrived. Again, I don't think these are the strong reasons to believe in particles or waves, but regardless, this is a pretty weak rationalization. Again, sort of quote mining evidence, or attempting to, and still failing.
Well, now I'll turn down the lights again, and we'll just show that with our Young's wave trough. In the first place, Mr. Coates has got a dipper, the one like those we used before, which gives very short waves. He's placed in front of that an obstacle which is of a fair size compared with the wavelength, and I think you will see that behind that obstacle there's quite a sharp shadow. Right, shall we start it going now?
Okay, so he says this is a wind, okay, when clearly the wave does go through, and you can see the bend in it, but it's straightening and straightening as it goes further and further out. And yeah, there's some shadow, but clearly half the wave is still intact, we could argue.
There, do you see the shadow behind the obstacle with these short waves?
Yeah, no, if you just straighten them out, you would see a little bit of a dullness, but it's not at all wiped out, anywhere close to wiped out.
Now, Mr. Coates is going to replace this dipper that makes the short waves with a very slow vibrator, which makes quite long waves. The same obstacle will be placed in the path, but I hope you'll see that the waves re-heal themselves and go on much as before. There, now...
It doesn't seem like much of a difference, right? I mean, the amount of loss of intensity seems pretty much the same, especially when you get out here. It doesn't seem much different in terms of the amount of shadow created. It's not substantially less shadow, so not a very convincing.
We'll set that dipper going. There are the long waves in the trough, and you see the obstacle.
It almost looks like more of a shadow, frankly. I mean, the cutoff, the lack of whiteness here, its brightness is pretty substantial.
Really is making practically no difference at all.
So he calls that practically no difference at all, when it's practically the same difference as the other one. So that's a pretty lame experiment.
To them. Right, could I have the lights up now? On the other hand, light does bend round obstacles to a small extent. I'll show that again with the same setup with which we showed the fringes. The young fringes, like as in his pinhole experiment. We've got again a lantern over there on my left with an extremely fine slit in front of it. This time we'll take away the double slit that we've got here and replace it first of all by a little shutter which I've got here, which has an extremely sharp fine edge on one side. And what I want you to observe is that the light does to a certain extent bend round this edge. and we'll then replace.
What the experiment will show is that this slit idea is kind of rubbish, that this is about surfaces. Because now he's going to use a single surface, and you're not going to see light bending. You're going to see light creating fringes. The same fringes, the same on-off, with just one slit, one surface, a half a slit. A half a slit is going to create the pattern that's supposed to be caused by Heisenberg and confinement of photons and all of this woo.
They're edged by this window here, in which we placed an ordinary sewing needle. And you'll see the rather pretty pattern made by the light which bends round the sewing needle. So now...
So again, he says the pretty pattern. So 1 minute the pattern is clinically fringes, and the next minute the pattern is just some pretty thing, and we won't even call them fringes anymore. I mean, it is kind of hilarious.
Go to my position for viewing these effects with my ground glass screen, and I hope to show you that light really does bend round corners. Well, I'll position myself again now so as to see these diffraction effects, and Mr. Coates turns the arc on and we turn the lights down. We'll replace the two slits that I had before by a window with a very sharp edge. Now, what I want you to notice is that on either side, really, the edge, there are effects which show the light is bending right into the shadow.
so it's just kind of funny. They're fringes, right? So they're the same effect as before, and now he's just calling them something else and saying they're bending around the edge, you know. When, yes, and that's, I would argue they're bending, but they're bending because they're hitting electrons. But the thing to really recognize is that what's really happening is that the surface gets lighter, you know, and then dark, and then light going out also, because those are where the photons are getting broken. I mean, you still have to understand, when there's a slit, single surface, what's happening is all the photons that go near that surface, almost all of them, have to end up getting broken. So it has to get very dark there. Because they're all getting broken. But they are getting reconstructed because there is a surface, a long surface. And a long surface means one can go from here to here. They can go this way, right? Because we did make it a deep well. There can be a piece of the photon coming from here and a piece that comes from here that can recombine. So you're not recombining just in this way, you're recombining this way.
You notice that just outside the edge, the light is brighter than it would be normally. Then again, outside, there's a dark line, and then it fades away into the general...
Right, so how would you explain that extra bright part? Right, because it's extra bright. And that doesn't make any sense. And then this one's extra dark, and this one over here is certainly extra dark. So, but if you did take all these things out, and you'd see that this one really is a composite of just extra light. All you've done from here to here is add extra light to these locations. So you made more photons, you didn't make less anywhere. There's no dark here. There's only dark, there's dark plus extra light. So you got some extra photons to land where on some surface that was already light. Some surface already light. Yeah, I think that's the right way to say it. This is the light side. And so you're adding more light going out into the light. Yes, that would be the way to say it.
Illumination.
But it's because you're taking it from the photons you destroyed, going right by the edge where the extra dark is.
Well, those effects are due to light which has come around the edge. It's an interference effect rather too complicated to explain. Fresnel first explained it. But
Too complicated to explain. I don't know. Okay, so we'll go see what Fresnel said. I'll have to go do that. I mean, it's a surface. So it will be interesting to see the wave theory of a single surface, right? I mean, it's a little harder to explain a flat surface creating fringes, right? I got a plane wave going in. I put a surface here, and the one surface somehow creates fringes. Well, no, that this way. That somehow the one surface creates fringes going this way. Into the wave. I don't know. And they're higher frequency fringes.
It shows certainly lights going around the edge. Now Mr. Coates will replace that window by one in which we've placed a needle. And here the diffraction effects are quite complicated. You must only see the bright line outside the shadow, but I think some other fringes, and a curious fringe right in the middle of the shadow of the needle.
Right, so there are the curious ones to me would be the ones way on the outside there. But that's because it's really got 4 surfaces. So it's really a double slit experiment. And so that's why you have 2 patterns separated by such distance, is because it's almost the inverse of the traditional 2 slit experiment, in that you have 2 outside surfaces and then the 2 inside surfaces, which is the exact opposite. They're facing out, they're facing in where they're tight, and they're facing out where they're further apart, which is exactly the opposite of the 2 slit experiment. So the envelope pattern is the one that's really wide, and the little pattern that was on the outside is now on the inside, creating the little bars.
Obviously, the light is not going dead straight. The waves are bending round the corners.
Alright, so he says the light is bending around the corners. It's clearly creating shadows. Even a tiny needle's creating shadow. So it's not bending around consistently, and it's creating a ton of interference patterns.
Have the lights up, please. Here's a very simple experiment you can try for yourselves. Look at a distant street lamp through a window and move your head so that the street lamp just disappears behind the edge of the window. Now, if you look, you will see that the edge has a bright white line along it, and you can see that even if you move your head.
Right. You can also do the 2-finger experiment, where they're not touching each other, yet it turns completely black before you touched your 2 fingers together. And you can see all the little lines and everything. So, yeah.
Quite a long way into a geometrical shadow, as it's called. This, of course, again, is due to light waves which have bent around the edge. Well, it was...
And bent in what mechanism, again? This whole argument about how exactly do you bend these waves around an edge? How does the wave know to reconstruct itself across the edge? What is it requires a medium, again, this glue thing that somehow just magically remakes the wave. There's no theory for how that happens in space.
Interference fringes like this, which led Young to assert that light must consist of waves. He was quite right. It started a new chapter in the history.
He was quite right, except, until he's wrong. And I'm just saying, if you really look at the facts and you admit what the truth is, he was analyzing the wrong pattern, and he didn't know what polarization was, and didn't know what electrons were, and didn't really understand any of these mechanics physically. He was boldly asserting something that he just didn't have enough evidence to assert, and you all jumped on that wagon, and the wagon is now in a purgatory of failure, and you either admit it, get it over with, and move on with a true story, or just keep compounding a lie that you're going to keep telling, that somehow you proved that it has to be a wave, when you never accomplished that task with anything called real evidence. The 1800 trial was a piece of crap, and looking at it in hindsight, the defendant needs a new trial and deserves one. And you either have the honor to give him one, or you be dishonorable bums and leave particle theory in jail that it doesn't belong in. That's how I'm looking at it. If you have some integrity, you'll fight for the truth. If you don't, you'll keep propagandizing for the lie.
Of optics. And the Royal Institution is proud that in the year 1800, Thomas Young was one of the professors here.
Well, you should be proud. He was a good scientist and all that kind of crap in a lot of respects, but it wasn't good science to make declarations that I proved something, and I'm not sure he even did that. But regardless, you're all saying he did, and he didn't.
And gave lectures in our theatre about these effects.
So this is the empirical version, right? the king's version of the truth, and it sucks. That's all you can say. As evidence, it sucks. So, it's a long video, blah blah blah, but I think all of this needs to be explained. Yeah, it's just who's the audience and what do they need to know first before, there's so much to physics you got to know first about just these simple mechanics of equilibrium and all kinds of different energy conservation, all these different concepts. So depends on really who's listening, what they need to hear, and that's unfortunate because I can't please everyone almost any of the time. This task is difficult, but I'll endeavor to persevere. I will do that.